Hey everyone, and thank you for joining us for the next session of our Startup Spotlight series. My name is Anna. I'll be your producer for this session. I'm an event planner for Reactor, joining you from Redmond, Washington. Before we start, I do have some quick housekeeping. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional and on topic. Keep an eye on that chat. We'll be dropping helpful links and checking for questions for our presenter to answer live. Our session is being recorded. It will be available to view on demand right here on the Reactor channel. With that, I'd love to turn it over to our speaker for today. Jonathan, thank you so much for joining.
Thank you. I appreciate being here today and joining you. I'm Jonathan. Just a bit of introduction about myself. I'm the co-founder and CEO of Moderne. Moderne has been in engineering tools and developer tools doing large-scale software refactoring, impact analysis, vulnerability repair in enterprise code bases that sometimes span into the hundreds of millions or billions of lines of code. I founded our company along with our co-founder Olga Kunzic about 6 years ago in 2020. So we started really before the advent of the AI era. And so I think we've got an interesting perspective on what's changed and what stayed the same over that period of time. For those that are listening in today, I, as a presenter, love questions live. I love audience interaction. This format isn't the easiest, I know, to do that because I can't see you and you can see me. I would say, however, if as we're going along through the content, you see something you have a question about, you want a little further information about, just post that question live. And we have folks watching for these questions, and I'm happy to actually stop where I am and answer them in place. And hopefully that would help you get the most out of it. The format for today, I'm going to walk you through a number of different types of agent tools that we're finding, different tools that we can use to improve one of three quantitative metrics, either token consumption for our agents, accuracy of their output and how we score that, and overall wall clock speed. But before we begin, why are we talking about this? Adopt, in terms of developers adopting AI coding tools and agents in enterprise software delivery life cycles, I think it's fair to say we're there. In all honesty, it's a bit surprising to me how fast we got here. Some of the largest organizations in the world, and I'm talking about regulated industries like banking, insurance, healthcare, have adopted AI coding tools, in some cases, essentially as a SaaS product, by allowing their interactions to interact with, large foundation model third-party APIs in unbelievable time. So I think we're entering in 2026, and even to this point in 2026, we're not quite all the way there, but I think the curve is going to shift quickly from adopt to improve cost. We've seen some early signals of that. You may have seen the Uber CTO say at the beginning of April that Uber had already spent through a substantial $3 billion Claude Code budget for the year at the end of Q1. I think that's the sort of wave that's coming next. Folks are going to try to figure out how to actually improve the efficacy and cost of these things. For me, I've been in developer tools for a long time. My experience with it goes back to 12 or 13 years ago working on engineering tools at Netflix. I went to Pivotal and worked on the Spring team for a number of years after that, and then, of course, I've started this company. And so for many years, I've actually been working on developer tools, actually trying to improve the efficiency of developer. At the beginning of this year, our company rebranded ourselves as an AgentTools company. And that was really meant to reflect what we see as the growing proportion of agents to humans in this workflow. I'm still very human-centric leader or engineering leader. I believe that a human is really the one driving the fleet, not the other way around. But because it's true that these coding agents or agents operating in our SDLCs outnumber us in many cases, as a company, as a tooling person, if I could improve the efficiency of one or the other party, where's the greatest point of leverage? The greatest point of leverage would be the agents. And if I say the person is driving the agents and I make the agents more effective, then by extension, I've made the person more effective. Too often recently, the start and end of a conversation in something related to software engineering is, can it be done with an LLM? Can it be done? And I think we really need to start entering this phase where we think just because we can do it with an LLM, just because it can do a task once correctly, doesn't mean that that's the right vehicle to do every single task in the software delivery lifecycle. So I think one of the ways I talk internally to my own team is to simplify the kinds of tools we're looking to build, is we're actually starting to look for ways to exchange GPU for CPU. In other words, we're like the frontier lab of GPU for CPU arbitrage, trying to find ways of offloading as much work off of that GPU as possible. I think what's clear is that there is a coming price shock. If I went back to this time last year, early 2025, and I'm just looking at a Claude Code, subscription-based usage limit sort of dashboard. I'm looking at my usage. If I went back to 2025, the planned usage's third of the screen was the only thing that existed on the screen. The weekly limits and extra usage did not exist. Somewhere around mid-2025, weekly limits snapped in, right? You may all remember, those that were using it at that time remember when that happened. And so when at the very beginning in early 2025, really I only needed to think about my 5-hour usage limit. How could I maximize blowing through that 5-hour usage limit and then resetting again, and continuing on. Once weekly limits came out, every you could consistently get through that 5-hour usage limit, but you're burning against that weekly usage limit as well. And when you burn through that, you're locked out for the remainder of the week. And it stayed that way until early 2026 when this extra usage toggle showed up. And I remember the moment that extra usage toggle showed up because there was a little promotion at the time where they say, hey, if you flip this toggle on, we'll give you, I think, $50 in extra usage if you flip it on before a certain day, right, and leave it on. And so I think it's fairly clear, and there's been a lot written about this, that this subsidized, subscription-oriented flat plan is going away sooner or later, right? And we've seen it kind of across the board, across the providers. It's just too expensive to run these things on the back end at the levels that the power users like myself and many others were really using them. So it's the way the price ultimately needs to be, one way or the other. And so it was at that point where we say, okay, if that price is going to shift, and before it does, and before everybody feels the impact of it, how can we start planning ahead to close that gap, to identify tools that would have to exchange GPU for CPU? And so we're going to go through, I think, what we've since kind of discovered and executed on in the 2 or 3 months since that transition. And hopefully this provides a good overview of the kinds of things that we think that agents can be given to be better at what they do in many ways. The first act, and probably the most obvious one, the thing you see a lot about, is just better search tools in the first place. Most coding agents use either an internal vector-based search or something like ripgrep or grep to do most of its searching. And those can be quite fast on their own, but either of those approaches actually does have a linear cost with respect to the volume of code that's being searched. So in terms of speed, in terms of it's ultimately going to be linear cost. There is another technology for code search that's not new on the market. Google's internal code search mechanism used an indexing format called Zoekt, Z-O-E-K-T, that was based on something called a trigram. And a trigram, without getting into the specifics of it, just understand that it's a mostly constant time search, irrespective of the size of the code base. The problem with a trigram search as the search mechanism that a coding agent would use is that there's an index that needs to be maintained. And so the coding agent is, of course, always changing the code. How do you keep the index up to date with the code as it's changing? And this leads to the first key trick, I think, in the toolbox of developing tools for agents, which is, how do I create a live process on the machine that the coding agent sees or is able to interact with while it's editing that code? And the trick is something that's actually lost a lot of popularity recently, and I think is underutilized, and that's the MCP protocol. Now, when people think about MCP, they normally think about MCP in terms of a remote MCP. They think of Salesforce exposing an MCP endpoint from its API, or Figma, or you name a SaaS provider that has a unique data source that wants to provide access to that to an agent. And that's certainly probably the most typical use of MCP. But there's another form, and actually the original form, which is a little bit less known, and that's that an MCP can actually be a local process on the machine that connects to the coding agent via STDIO. So no socket open, no internet connection open, no remote connection open. And that, in fact, can be configured on a global basis on a user's or a developer's machine. So you can configure, for the most part, for the coding agents in some place in a user home directory, a configuration that when any coding agent session launches, it also launches a local MCP process that it connects to via STDIO, and that remains alive for the duration of that coding agent session. The life cycle of that MCP, that local MCP, is tied to the life cycle of that coding agent session. Now, if you think the way I do, you think, a process that's running locally, that's connected to the coding agent session, that sounds like essentially an application server with a really well-bounded lifecycle. And it's that trick. So say I am able to connect an MCP, and a lot of the tools that we're developing now are surfaced in this way. I connect a local MCP to a coding agent session. Then as the coding agent is iterating and modifying code, that MCP could actually be using a file watcher to update an index. So this example of Trigram, this way of providing a trigram-based search, is achieved in this way, that our Moderne MCP or Mod MCP that's installed globally on the machine is basically doing a file watch as the coding agent is modifying code, continues to build up that trigram-based search or trigram-based index, and then exposes a tool to the coding agent for what we call Trigram, for the coding agent to use to do a more efficient search. Of course, it's faster on just like rote performance because it's a constant time search, but more importantly, there's another thing that a trigram or trigram-based search can do to help an agent be more effective at search, and to first kind of like understand why. When a coding agent does a grep or it does a vector-based search, you'll often see it do that search and then follow that up immediately with read, or blah, 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 blah. Why is it doing that? Say a coding agent was trying to look for a logging library like SLF4J in the Java ecosystem. It was trying to look for all logging, log.info calls to SLF4J. It may reasonably do a grep for that info keyword, but it's all the logging libraries, whether it's SLF4J or JUL or log, they all kind of look the same, right? So at the textual level, log.info isn't actually enough information for me to determine whether this is SLF4J or it's log4j or it's something else. What then winds up happening is the coding agent has to read this whole file. It's looking for evidence that log here, this variable in front of info, is actually from the library that I'm expecting. And if it isn't, then it discards the result. If it is, it adds to its result. And so that's that grep read pattern that you see. What a trigram index does often support is also adding symbol information to the index. So symbol information here would be information about this method, info, and what its declaring type is, that it's from S4J, that it's from JUL, and what its arguments are, and so on and so forth. So that would be what we call type attribution information being added to that index to help it match. So when a coding agent reaches for a simple base trigrep search, it's able to actually search not just for something called info, but it's able to search for SLF4J info, and the result that it gets back is already printed down to the set of matches that it's going to need, and therefore it doesn't have to do that subsequent read. That's the sort of key advantage there. The next type of search pattern requires us to talk first about the different kinds of representations of code itself. So code, as a coding agent typically looks at it, is textual, right? So when it does a grep, it's doing a text-based search. Some of the most advanced organizations that we encounter are trying to find ways of basically attaching the abstract syntax tree, so the more structural syntactic information about a code base, to the coding agent. They're trying to surface that. You'll see this in Anthropic's own recommendations recently to try to attach language server protocol, which was designed originally to serve IDEs like VS Code as the representation of code that you serve to a coding agent. But that abstract syntax tree representation of code has a couple difficulties. One, if we go back to the problem we just discussed about log.info, remember this? If I knew only enough information about the syntax of the code to know that this is a method called info, I actually still don't have enough information to determine whether it's SLF4J info or it's from some other library altogether that just happens to be similarly shaped. So when a compiler is ultimately producing whatever its end state output, whatever binary output that produces at the end, if it does, it goes through these phases where it turns text into abstract syntax tree, but it doesn't stop there. It goes through a next phase, which is symbol solving, where it's going through that AST and it's looking at all the libraries and all the other information available to it, and it's deciding when it sees a method invocation, who's the declaration or declarer of that method. When it sees a type or a symbol, it's deciding what is the type of that symbol. And this helps it actually write out the sort of end state binary representation that it's ultimately looking for. If you think about the additional data that a compiler would add to the abstract syntax tree, those are kind of the yellow nodes here on the right, but then also go back and pick up all the original white space and all the original comments and all these things that compilers discard early and stick those on the tree as well, you wind up with a representation that we call, and this has been a term we've used in the OpenRewrite open source ecosystem for many years, we call this a lossless semantic tree. It's called lossless because from this tree, you could visit the tree and print it back out to the text of the code, without any loss of information. It would have all the original white space, all the original comments, and so forth. It would look identical. So part of what we need to prove if we're going to have a coding agent interact with data at this level is that we can round trip between the text through the abstract syntax tree to the lossless semantic tree and then back to the text again faithfully. So this has been a lot to say, but we'll just say that this lossless semantic tree data, which is all the syntax plus all the types that the compiler knows about, plus all the original white space and other metadata that's stuck on it, is the key data source that underpins what ultimately needs some sort of access pattern to get to that data underneath it. And so that access pattern is something we call a recipe. And a recipe, and I mean specifically in a recipe in the terms of an open source framework called OpenRewrite, a recipe is a program that can iterate through that lossless semantic tree and make changes to the tree or mark the tree with search result findings in order to make a change to code or do an impact analysis of some sort. And so imagine in the OpenRewrite ecosystem, there's tens of thousands of these recipes that deal with transformations on Java code bases and JavaScript and C# and Python and JavaScript and infrastructure as code and Terraform and Kubernetes and so on and so forth. If you have thousands of these recipes that do small and large things to the code, and you could expose all of those recipes to a coding agent, then that's a different set. The coding agent's able to interact with the code at a different level than just repping and reading through the code. So here's an example of a Copilot session where I started the Copilot session in a particular repository, and I just asked find Spring API endpoints. Now, a coding agent could do that normally by grepping. It's going to try to internally say, what does Spring API endpoint look like? It has a particular annotation on it, or it has a particular XML configuration, whatever the case might be. In this case, when that MCP server exposes all of the OpenRewrite recipe marketplace to the coding agent is able to reach for one of those recipes to quickly answer that question. So here you see it reached for 3 successive find annotations recipes to ultimately derive this table of all the Spring endpoints that exist in the repository. And as you might guess, that recipe is a CPU-based tool, so the only tokens that were exchanged here was just the model looking basically at the recipe catalog and saying, I want that one, and executing it and waiting for the result to come back to it fully formed. It didn't have to go grepping and reading its way through the entire code base to get to this answer. This is just one example, find annotations, but again, imagine thousands and thousands of these recipes being exposed, provide different levels of access to the data that we're interested in. I think this may be getting a little bit deep, but I think that there's another interesting pattern that we see in another opportunity area for providing Trigram or Trigrep-based code search to, and that's the dependencies that our projects depend on. Commonly, I see, if I dig into subagent logs enough, what I see coding agents do when they're trying to reason about the way my code works is, well, my code is dependent on third-party and open source frameworks and libraries and tools. In fact, some folks say 80 or 90% of an enterprise code base really is the third-party or open source dependencies upon which it relies, and the business logic of the application is just kind of glue code, stitching all these different components together. So a lot of the actual code that we ship is coming from outside the source code that coding agent is looking at. When I see a coding agent trying to reason its way through how a particular piece of business logic works, I see this pattern quite often where it will take a binary dependency, create a temp file on disk somewhere, actually extract out like in this case, a jar, it's unzipping the jar into that temp directory. And then it's actually using Java P to read the bytecodes of the dependency to try to understand the business logic of what that thing is doing. This should sound kind of crazy. Like this is never the way humans have understood our binary dependencies. What do we do when we want to understand? IDEs often, in fact, most of the time, when we want to click into a library to see how it's functioning, it's at that last moment when we click into that library that an IDE will actually download the source artifact for it and then open it for us to reason about the code itself. We don't read the binaries, right? That's crazy. That is something that coding agents don't do. They really just brute force directly read the binaries in most cases. So there is an opportunity here, and the opportunity is at that interaction point between the build tool, which the coding agent's interacting with. And I mean by that, I mean like a Maven, Gradle, an NPM, a PyPy, whatever the build tool might be for the language, and the artifact repository, where dependencies are being resolved from. That if the artifact repository exposes essentially a trigrep type index of the source code of the dependencies that were pulled through, then that would be a tool that could be exposed to the coding agent to reason about this in a much more sensible way than just trying to rip apart the bytecodes. For us and for Moderne, we expose that as a proxy to your artifact repository, at least at this point. So we'll put something between the coding agent and the coding agent's interacting with the build tool, put something between the build tool and the artifact repository prop that you have, so that as it's pulling through binary dependencies, we're also trigrep indexing them and then surfacing those to the coding agent to use at its discretion. I think we've beaten to death the sort of code search act one here. And that's, it's again, just the first tool, the one that's most obvious that people think there's an opportunity in. Act two is something called Prethink, or I'm going to call it Prethink. I'm not sure what the total, what the industry is going to settle on, the term it's going to settle on, but a lot of people talk about context registry and context as an important part of making agents more efficient. The first question I think to answer is, where should context lie? If we're going to expose context to a coding agent, where should it reside? And I think we've all seen products like this. We've seen Devon's Deep Wiki. There's many different products that are saying, hey, we'll build a knowledge graph. Hey, we'll build a wiki. We'll use AI to read your code and build a markdown summary of what it is, and that'll make the coding agent better. The first question then is, where does the output of that, however it's derived, reside? One obvious answer is that it should reside in the repository itself. And I've seen a couple different approaches to this. One is to commit it to the repository itself as an artifact or as just another source file. Another option is to use a technology called Git Notes, which is not super well known, but you're able to attach metadata to artifacts or source files without them being seen by a normal Git clone. There's going to be some folks that say, hey, the context registry should be the artifact repository. And then I think there's going to be a third population, and indeed these do exist out there, who's saying that the context registry itself should be a third system of record. If you think of the systems of record in software delivery lifecycle being version control system, your GitHub, your whatever it might be, your artifact repository, that's your Nexus, your JFrog, your PyPy NPM sort of thing. I think there's going to be a lot of folks that want to sell a third system of record because those, frankly, are very sticky in the enterprise. So I would be cautious as you think about context registry to think, is somebody selling me another context or a system of record because they have an incentive to do so, or is that because that's the way to do it? We weren't originally involved in this space, and I would say a couple of our, especially large banking customers, did evaluate many of these and said, look, we would prefer that context be stored in the repository itself, or at least this was the original thinking. And so you have all these recipes that can emit data, and OpenRewrite recipes can emit structured columnar data in addition to changing code. Could you just run those recipes and commit the results of those tables, the data, back to the repository itself, so that the next time a coding agent session launches, I don't even really have to do anything. I don't have to have a skill. I don't have to have another plugin or anything. It's just the context that the agent needs is resident right there in the repository that the agent's looking at anyway. And this is where Prethink came to life originally. To show the impact of it, it looks something like this. Say I'm in a coding agent session. I took this example here where I had a repository and it said, if I modify the order entity, which is some business object in this repository, what other services might be affected? And just like we described before with grep, you'll see the coding agent exploring and reading and grepping and all this stuff, trying to understand how the project's stuck together, consumes who knows how many tokens, 60,000 tokens in this case, small repository, luckily. Took about 2 minutes and ultimately comes to a conclusion about what impact it would have if I modified this entity. So I took this, cleared the context altogether, cleared the get history, and ran this OpenRewrite recipe that produced Prethink context. Remember, we're thinking about a deterministic CPU-bound tool that emits structured data in the forms of rows and columns of information, of evidence for the architecture of the application, for the dependencies of use, the coding styles, et cetera, et cetera. And we check those back into the repository itself. Then if we launch another coding agent session and ask the question again, if I modify the order, any what other services might be affected, the coding agent actually reaches for Prethink context. It sees in the repository itself, and in 5 seconds has an answer. And of course, the interesting thing to me about this is that the context itself that's provided back to the agent should be layered and should be configurable. I'm not a big fan of the let an AI agent run through a code base and just pick out arbitrarily whatever it thinks is interesting about my code base and slap it into an unstructured markdown file. I think the more interesting thing is if you could have tools, statically determinable tools, that produce evidence of particular patterns you're interested in, and that you could basically add additional ones so that the context your agent sees is the context you wanted to see, and that it doesn't cost tokens to produce that context. If it doesn't cost tokens to produce that context, it's something that you put into some sort of automation loop every night or every 6 hours or whatever, and just always keep the context in the repository current with whatever the current state is. Act 3. So Act 2 is a little bit shorter. We had a lot of the background information all together. In Act 3, we're building on this just a little bit more. So you may have thought, okay, if a recipe can do a search, and recipes were originally designed to do edits, what if I could expose recipes or deterministic programs that are able to do large and big things in code to a coding agent so they can use that rather than its very blunt tools of just directly writing code. So to look at first, we haven't really had a chance to dig in. There's too short of a session to dig in too much to recipes here, but just understand that in OpenRewrite terms, a recipe can be very compositional in nature. At the point when I had taken the screenshot and we were still doing a lot of Spring Boot 3.4 migrations, that recipe had 3,300 individual steps to it. So to migrate to Spring Boot 3.4, you first have to get to 3.3, which means you have to get to 3.2, 3.1, 3.0, Java 17, it means you have to Java 11, it means you get to 9, which is the 8th. So like, there's many steps that go into coding tasks of the sort that we see with application modernization or vulnerability repair or whatever the case might be. And so these steps are each individual recipes. Every little dot you see in this directed graph is its own recipe, but they are all kind of stacked together into what it means to do a Spring Boot 3.4 migration, and it's become a deterministic machine that's good at doing that specific business-shaped problem. Now, remember we had this local MCP thing we talked at the beginning. This is your power of being able to launch a local MCP process alongside a coding agent that exposes all these recipes to a coding agent to use at its discretion. I launched a coding agent session in one of our repositories and just said, upgrade to Java 25. And that's a fairly complex task. So the coding agent actually, you see it searching for recipes right now. It says, okay, I'm going to look for whether there's a tool that's shaped to the business problem I'm interested in. And sure enough, it finds this upgrade to Java 25 recipe. It learns about it. So the next step is in the chain is really that the coding agent would read more information about it, understand what data table output it could get out of it, understand what kind of changes it's going to make, and then ultimately it decides to run it. So that third step here you see where it says preparing recipe is the model has decided to execute that recipe. About 2 minutes later and 30,000 tokens later, most of this migration is complete. The migration has touched 700 files so far. It's consistently applied these patterns that it's kind of the coding agent summarized for you here, that it's gone through and found every instance of pattern match. It's replaced unused variables. It's done all this kind of thing. And in some cases, there's hundreds of those occurrences, right? So just that first pattern here, instance of pattern matching, there was 352 files that needed to change, or that should change to adopt this new idiom as I'm moving towards Java 25. For any of you that have used coding agents often through your workday, I think you'll probably agree with me that we jointly have the experience that when you ask an agent to do the same task many times, the outcome is usually, okay, I'll go find all those occurrences. And it does a search and does this kind of thing. It says, okay, I'm going to go do it. And it'll declare success sometime later, and you'll go look and you'll find, well, hey, it did a lot of them, but it didn't do all of them. I call this problem the problem of chasing residuals. Is residuals being these leftover, I should have actually changes, but I didn't. I think there may be something fundamental to the way these work. I think that coding agents are often used for net new authorship. Like we use it to do feature development. And when you're doing feature development, you kind of don't want to touch the whole code base usually, right? You want it to be as limited in scope and tailored to the problem area that you're trying to address as possible. You don't want to just rampage through the whole code base and change everything while you're adding a simple feature. On the other hand, when I'm trying to do something like this, when I'm trying to fix a vulnerability consistently, when I'm trying to do a migration consistently, that's sort of at odds with the experience of feature development, which is that it has broad impact on a large portion of the code. And so pretty much without exception, I find when I'm trying to do many of the same thing, a coding agent will not successfully chase all of the residuals. Now you could, of course, say do more, and it'll keep chasing more and more and more of them, but you're never totally sure when you're done altogether. At any rate, aside from the chasing residuals, keep this in your mind for a moment, that that the coding agent choosing to use a recipe or a tool that's in the shape of the business problem here took about 3 minutes and 30,000 tokens in this particular case. So I actually, again, wiped the context, actually uninstalled all of the coding agent tools, and I asked and went back to the same repository, reset the history, and asked it to do the same thing. I said, upgrade to Java 25, same prompt. It updated the build file only, didn't touch the source code, and declared itself successful. And so I said, wait, I mean, you missed the bulk of the work, right? Which is to actually uplift all the source code to the latest gen of Java 25 coding patterns. Of course, you're right, build dependency updates are just the trivial part. RealWorks updating all this stuff. Let me explore what it means. And explore means it's going to launch plan agents. It's going to launch plan agents. It goes out and reads OpenJDK, JP512. It's going to go read blogs on it. It's going to go read other. what it's basically trying to do is discover this. What is the shape of the business problem that I'm trying to solve? At some point, launches more plan agents, comes to some conclusion. Ironically, it discovered the technology. I had founded it, and we've been talking about it. I founded Netflix many years ago called OpenRewrite. This is, again, a deterministic system to provide these sort of transformations. Coding says, maybe I'll just run OpenRewrite, right? I said, look, like we're trying to show like GPU versus CPU here. So I actually selected number 2 here. No, you make direct code changes, right? You're supposed to be able to do all this yourself, after all, right? And so it says, fine, I'll work one pattern at a time across the entire code base using grep and replace. And so we think, oh no, not grep again, right? Like we're gonna, it's gonna be the same kind of situation. Makes a bunch of sort of grep and edit sort of replacements here. Of course, there's complexity to these patterns. So even something like instance of pattern matching is a little more subtle when the instance of was negated. Then you can't negate a pattern match. So that actually has to be left alone. So it kind of trips over those and works through many of those scenarios. About 45 minutes later, I canceled the session. I was giving this talk originally at Microsoft AI Tour London. I had to get up on stage in 30 minutes. I couldn't wait for another hour. At that point, it had completed about 4 of the 15 tasks that it identified as key to that migration. So about 1/3 of the way there, generously, and at this point had consumed 61 million tokens. That's the problem. Is we're saying it's 45 minutes in, it's 90 minutes in, whatever the case might have been at the end. It wasn't 30,000 tokens, it was 61 million. This is one repository. Even if I pressed it and egged it on to completing this migration all the way through, chased all the residuals, in the enterprise, I'm thinking of one of my banking partners that has 200,000 repositories under management. This is one. This is one out of 200,000. So part of what I like about providing recipes, basically tools that are shaped to the business problem, is once I've sort of figured out what that form is, and I allow a coding agent to use that form to stamp out an outcome in a particular way, I can reuse it. It's like making a cookie cutter to make very low variability, highly accurate cookies many times over again across all 200,000 of those repositories. The question then becomes, who's writing the recipe? And increasingly, what I'm finding, and I think is kind of this beautiful symbiotic relationship, I'm using the coding agent to write the recipe that I validate, that I write unit tests, that it writes unit tests against, that we go exercise on a set of repositories in a business unit and get feedback and write additional unit tests and catch additional edge cases until it's almost like carving out of a raw piece of marble. The whole sculpture emerges of what the shape of the business problem is, and then that becomes the tool that it then goes and stamps the same shape out over and over and over and over again consistently across the code base. This is how I feel we're going to answer the bell for something like a Mythos. That is going to discover the shape of a problem, the shape of a vulnerability, the shape of that needs to be remediated in some way. And I feel like whether it's an OpenRewrite recipe or something like it, we need to provide deterministic CPU-bound tools that can pair with the shape of that problem to ultimately, consistently apply it across the code base. And that's I think, that's Act 3. I'll end with one more, but I'd say that there's certainly not only 4. There's many opportunities, I think, to provide different types of tools to coding agents ultimately. I think the next opportunity that's very interesting to us is around the chat transcripts themselves. To find and extrapolate patterns of what coding agents are doing, to discover what the next tool is that could make the biggest difference ultimately. So if you remember this chart from the beginning when we were talking about Trigram, where I was talking about the difference in efficiency between a grep and a Trigram search on any given occurrence, I think that there's just an opportunity to watch what a coding agent's doing and ship all that information somewhere. Basically collect it internally inside your organization and overlay those transcripts on organizational structure. Something we do with all of our enterprise customers, one of the first things we do in onboarding is prepare it's actually a CSV. We list every repository in an organization. And in one of the columns of the CSV, we say what team does it belong to? And the next column is what org does that org report to, and so on and so forth. However deep that is inside an individual organization. Everybody has some mapping of that, but we put it in this form, this sort of tabular form. If I could overlay chat transcripts from developers on that work on the repositories on a team, on those teams themselves, and look for common patterns, I think that there's a lot of opportunity there. The first thing that we've actually layered on top of this organizational structure for ourselves, actually simpler than the transcript, is just every commit and every PR happening, across our team. I've got a relatively small company, but still about 30 developers altogether. We have about 400 repositories, and I can't keep track of who's doing what. I honestly can't even keep track of what I'm doing on any given day. So being able to go and select that organization, that just the OpenRewrite organization, or just the Moderne SaaS team, or the whole business as a whole, and seeing who's doing what, who's committing what, who's opening what PR, who's forgetting what PR they open, that organizational overlay, I think, provides a lot of value and information. So I think there's a lot of opportunity around mapping activity from chat transcripts back to the organizational hierarchy that those transcripts are affecting as well. I'm happy to take time to answer any questions. I would love to hear what you have.
Jonathan, we've had a pretty quiet chat today, but just a reminder for everybody tuning in, if you do have any questions, just drop them in the chat and we can pass them right along.
Great. I'll stop the screen share in the meantime.
I'd say we can give it another minute.
Okay.
And if we don't have any chats by then, I think we can wrap up. But I just want to say on behalf of the Reactor team, thank you so much. That was a fabulous session, absolutely fascinating. We do have a comment from Daniel in the chat that just says interesting. It was very interesting. So thank you, Daniel, for that.
All right. I don't think we're going to get any questions today, Anna. So I very much appreciate you having me, and I'll let you take it from here.
Awesome. Thank you. We can't wait to have you back.
Bye now.
Thank you all for joining, and thanks again to our speakers. This session is part of a series. To register for future shows and watch past episodes on demand, you can follow the link on the screen or in the chat. We're always looking to improve our sessions and your experience. If you have any feedback for us, we would love to hear what you have to say.
You can find that link on the screen or in the chat. And we'll see you at the next one.